Throughout history, our knowledge of space was extremely limited. Of course, it still is. 400 years ago, few people even knew that Jupiter has moons revolving around it. Now we've discovered planets orbiting around our nearest stars. These discoveries were made with telescopes, and if it weren't for telescopes, we'd be almost completely ignorant of what's beyond Earth. It's important to understand what's around us. Long-term survival of humans depends on it. And to see almost anything beyond our solar system, we need big telescopes. I'm going to provide an overview, a summary of a concept for a potentially huge space telescope. First, I want to make a couple of comparisons. Certainly, the Hubble Space Telescope has been incredibly successful. With a single mirror that's less than 3 meters in diameter, it's given us amazing views of space such as this, and it's enabled many scientific discoveries. Now, the James Webb Space Telescope is designed with 6 times the light-gathering power of Hubble. It's a significant advancement. Technologies that make this possible include a large segmented primary mirror and adaptive optics. Existing designs, such as the James Webb, require assembled structures to be fit within the payload shrouds of their launch vehicles. Then, once in space, these telescopes are unfolded by mechanisms. So, there must be extreme reliability of many moving parts, and this is achieved with high-quality components, testing, and redundant systems. Many of these components and systems have nothing to do with astronomy. It's unfortunate because the costs of these items limit the sizes and the capacities of the telescopes. For the concept I'm proposing, construction of the major structures will be done in space. In addition, the mirror positioning system will be simple and affordable. These characteristics enable it to be scaled to a huge size. It can be more powerful than any telescope that's now planned for Earth or space. It could be enormous. Any name for this needs to distinguish it from telescopes that are just extremely large. So, I'm calling it the Ginormous Space Telescope. Although it's bigger, some aspects of this are similar to other space telescopes. As with the James Webb, it will most likely be placed in a solar orbit about 1.5 million kilometers from Earth. Some of the optics and systems can use existing designs and technology. However, to be significantly larger, this telescope will have to be different to be affordable. Because it is constructed in space, it can be larger than anything that needs to be assembled and then packed into a launch vehicle. Also, costs of mechanisms to unfold the structures are avoided with assembly in space. To assure efficient construction, this concept uses simple, snap-together connections whenever possible. Many of the connections can be made without fasteners using permanent magnets bonded to structural members. Beam elements and components can be designed with low mass since they'll be transmitting small loads. Like other large astronomical telescopes, the Ginormous Space Telescope has a segmented and adaptive primary mirror. However, the concept solves size limitations of other designs. It enables an extremely large primary mirror because of the simple and low-cost way it positions the mirror segments. A patent for this is owned by the Boeing Company and is titled Adaptive Reflecting System. This states the need for a mirror system that, quoting from the patent, can provide massive light-gathering capacity while allowing for compact stowage in a spacecraft payload compartment. That's what the Ginormous Space Telescope does. By the way, while I'm the inventor and I worked for Boeing when the patent was filed, there's currently no affiliation. As a rough concept, the precise size of this telescope isn't important, but I've modeled it with a total surface area of approximately 1,000 square meters. At this size, it has 40 times more light-gathering power than the James Webb, and it will be much larger than other proposed space telescopes. It will be even larger than the Earth-based European Extremely Large Telescope. And not only will this concept collect more light, its performance won't be affected by the atmosphere. I'll describe the concept. One end of the spacecraft will always be sun-facing. This is the aft side. The primary mirror is positioned forward of a sunshield. Almost everything on the forward side will have a black optical coating. On the aft sun-facing side, the sunshield will have reflective panels to block sunlight from the optics. Aft structures support a laser that will be used to control positioning of the primary mirror segments. I'll explain how it's used after pointing out a few more things. For this simulation, dark components are shown lighter than they'll actually be so they can be visible. Mirror segments have a gold color. Forward of the primary mirror is the optics and instrument module. An Earth-pointing communications antenna is mounted to the aft structure. The forward end of the telescope holds the secondary mirror assembly, which returns light to the optics and instrument module. The secondary mirror is supported by long beams. I'll provide a little more detail, and I'll start with the primary mirror assembly and some of the surrounding components. Each mirror segment is mounted on a spherical bearing that's secured to the mirror assembly frame. The bearing provides freedom of movement so the mirrors can be precisely aligned. While this concept model shows circular mirror segments, they could be hexagonal. Space between the sunshield and mirror assembly contain the spacecraft bus. This is a module that holds instrument and spacecraft control systems. Beams are also in this area to separate the primary mirror from the sunshield. These beams form integral trusses when connected to the mirror and sunshield structures. In addition to being parts of the mirror backing, the trusses connect to the aft structures and secondary mirror supports. The aft side of each mirror segment is connected to a long, slender rod that extends to the sunshield structure. This is for positioning control of the mirror segments. These rods are very thin and don't show in the model. Low-mass beams are snapped together to make the sunshield structure. Node points of some of these beams hold small devices to control the position of the mirror segments. After the structure is assembled, the reflective panels are snapped onto the beams. This concept model has 560 mirror segments, and each of these are 1.5 meters in diameter. With so many segments, having complex and expensive mirror positioning controls really wouldn't be practical. The adaptive reflecting system patent addresses this with a simple, low-cost method to control the mirrors. It makes this concept feasible. Here's generally how the controls work. As I mentioned, node points on the mirror assembly frame have spherical bearings. These bearings hold the mirrors and allow a gimbaling movement. This shows the back of a mirror segment, a bearing, and part of the frame. The end of the positioning rod that's opposite the mirror connects to a thermal actuator with a permanent magnet that acts across a small gap. This gap allows the assembly to slightly rotate. Red parts in this image are magnets, and a thin non-ferrous membrane is shown green. The thermal actuator is held onto the other side of the membrane by the magnets. When the actuator moves across the membrane, the rod connected to the mirror segment also moves. The laser that's mounted on the aft structure directs light onto the thermal mirror positioning devices. A tracking scope can be mounted with the laser to provide machine vision to precisely direct the light. The positioners get energy from the laser, so no wiring is routed to the actuators for either power or sensors. When a mirror segment needs to be realigned, the laser is directed at the thermal actuator. This device is a simple heat engine that makes small movements in response to the laser light. When the optic systems detect misalignment of a mirror segment, the laser is pointed at the device to cause the needed movement. This shows one of the actuators mounted on the sunshield frame. As you can see, these are simple devices. They're inexpensive to manufacture, as most of the parts can be 3D printed by laser sintering of metals. Then they're bonded or snapped together as a subassembly while still on Earth. I'll briefly summarize how they operate. In the patent diagram on your left, the green item is the non-ferrous membrane. This is the positioning rod. All parts with a blue color are ferrous, so they are attracted to the magnet shown in red. There's a small center assembly and a larger outer ring assembly. Both are held to the membrane by the magnets and friction, so this is probably easier to see in this cross-sectional view. Due to the arrangement of the magnets, friction is lower for the center assembly when it is heated by the laser. This has a switching effect that's needed for the actuator to operate. The laser will either heat the center assembly or the outer ring segments. These ring segments are made of nitinol, which has a high thermal expansion coefficient. The result is that the laser energy produces controlled movements of the actuator across the membrane. It's nothing magical, and I won't go into the details, but when the actuator is caused to move, the rod follows it and the mirror segment is adjusted. Well, I just wanted to give an overview of how mirror positioning works. Of course, the patent describes this more thoroughly. This concept for positioning the mirrors, along with a design that can be efficiently assembled in space, makes it possible for this telescope to be extremely large. I appreciate your time. This could become a funded project with support from a private investor or a government space agency. The technologies exist, so it'd be great to see at least some form of this in space.